The world is in the midst of a pivotal shift towards renewable and sustainable energy sources. One of the most promising contenders in this global energy transition is green hydrogen. Meanwhile, parallel to this energy transition, advancements in technology are also reshaping numerous sectors. One such advancement is 3D printing, which is transforming industries from medical to manufacturing. The intersection of these two pioneering fields, green hydrogen and 3D printing, holds significant potential for sustainable industrial development. Overview of green hydrogen. Green hydrogen is a form of hydrogen fuel that's produced through electrolysis powered by renewable energy sources, like solar or wind power. Unlike gray or blue hydrogen, which are produced from natural gas and emit carbon dioxide in the process, green hydrogen production is essentially carbon-free, making it a truly clean energy source. The appeal of green hydrogen lies not only in its sustainability but also in its versatility. It can be used across a wide range of applications, including heating, electricity generation, and as a fuel for transportation. Furthermore, it can be stored and transported relatively easily, providing a solution for one of the biggest challenges in the renewable energy sector: energy storage. Overview of 3D printing. 3D printing, also known as additive manufacturing, is a revolutionary technology that builds three-dimensional objects from a digital file. It works by successively adding material layer by layer, hence the term additive. This is in contrast to traditional manufacturing methods which often involve cutting away excess material. Since its inception, 3D printing has opened up a world of possibilities for various industries. It allows for rapid prototyping, customization, reduced waste, and even complex geometries that would be impossible with conventional manufacturing methods. However, 3D printing processes, especially at an industrial scale, can be energy intensive. Consequently, the need for sustainable energy sources to power 3D printing operations is becoming increasingly crucial. In the following sections, we will explore how these two innovative fields, green hydrogen and 3D printing, can intersect, the potential benefits of their integration, and the challenges that need to be overcome to make this a reality. The intersection of green hydrogen and 3D printing. As we navigate the uncharted territories of the 21st century, the intersection of innovative technologies like 3D printing and sustainable energy sources such as green hydrogen provides an opportunity for achieving unprecedented levels of efficiency and sustainability. The fusion of these two domains promises to revolutionize industrial processes while contributing to the fight against climate change. The need for sustainable energy in 3D printing. While 3D printing holds immense potential to transform the way we design, create, and manufacture, it is not without its drawbacks. One of the significant challenges associated with 3D printing is its high energy consumption, especially in industrial scale operations. This is particularly true for techniques like selective laser sintering, SLS, and direct metal laser sintering, DMLS, which require substantial energy to melt and fuse materials. This high energy demand, if met by conventional, fossil fuel-based sources, could result in a substantial carbon footprint. As such, the industry faces growing pressure to adopt more sustainable energy sources. Additionally, in off-grid locations or places where energy supply is inconsistent, finding reliable energy sources to power 3D printing operations is crucial. This is where green hydrogen comes into the picture. The potential of green hydrogen. Green hydrogen could offer a solution to the energy challenges facing the 3D printing industry. As an energy carrier, green hydrogen has a high energy content by weight, making it highly effective for energy-intensive applications. Furthermore, when used in fuel cells, green hydrogen can generate electricity with water being the only byproduct, making it a clean, sustainable solution. The potential benefits of green hydrogen extend beyond merely providing a sustainable energy source for 3D printing operations. For instance, the water produced as a byproduct of hydrogen fuel cells could potentially be used within the 3D printing process itself, particularly in binder jetting technologies that use a liquid binding agent. This would contribute to a more circular economy, further enhancing the sustainability of the 3D printing process. Moreover, hydrogen fuel cells' modularity allows them to be scaled to the exact energy requirements of a 3D printing operation, improving energy efficiency. They can also provide reliable power in areas with an unstable electricity grid, opening the door for 3D printing operations in more remote or less developed regions. By integrating green hydrogen into 3D printing, we could therefore usher in a new era of sustainable manufacturing, aligning technological innovation with environmental responsibility. However, realizing this potential is not without its challenges, which will be discussed in the subsequent sections. Integrating green hydrogen in 3D printing. As we venture into harnessing the potential of green hydrogen in 3D printing, it's essential to identify how this integration can take place. This mainly involves the incorporation of fuel cell technology, the application in energy-intensive 3D printing like metal 3D printing, and the potential to establish a closed-loop system. Fuel cell technology and 3D printing. One possible method to integrate green hydrogen in 3D printing is through the use of hydrogen fuel cells. Fuel cells convert the chemical energy stored in hydrogen to electricity, with heat and water as the only byproducts. This electricity can be used to power the 3D printers. Fuel cells offer several advantages. Their modularity allows them to be scaled up or down to match the energy needs of the 3D printing operation, leading to improved energy efficiency. Also, their ability to provide steady, uninterrupted power makes them an attractive choice in regions where the electricity supply may be inconsistent. Green hydrogen and metal 3D printing. Metal 3D printing, particularly processes like selective laser sintering, SLS, and direct metal laser sintering, DMLS, are notoriously energy intensive. These processes involve using a laser to fuse small particles of metal into a solid object. The amount of energy needed to generate the heat required is substantial. Green hydrogen could provide an energy-efficient and eco-friendly solution for these operations. By supplying the required energy via fuel cells, green hydrogen could help mitigate the environmental impact of metal 3D printing, contributing to cleaner, more sustainable industrial practices. The potential for a closed-loop system. Another exciting potential of integrating green hydrogen in 3D printing is the possibility of creating a closed-loop system. In a hydrogen fuel cell, the byproducts are heat and pure water. The generated heat could be utilized to maintain optimal temperatures in the printing environment, while the pure water could find use in 3D printing processes like binder jetting, which require a liquid binding agent. Creating such a closed-loop system would not only make the 3D printing process more sustainable but also improve its efficiency, as less energy and resources would be wasted. This is a compelling example of how the combination of green hydrogen and 3D printing could further the goals of a circular economy. In conclusion, integrating green hydrogen in 3D printing holds significant potential. It promises to enhance the sustainability and efficiency of 3D printing operations, especially energy-intensive processes like metal 3D printing. While the road to achieving this integration may still hold some challenges, the potential benefits make the pursuit worthwhile. Challenges in implementing green hydrogen in 3D printing. While the prospects of integrating green hydrogen in 3D printing are promising, the road to realization is not devoid of obstacles. The two main challenges that come to the forefront are related to cost and infrastructure, and safety concerns. Cost and infrastructure. One of the most significant barriers to the integration of green hydrogen into 3D printing operations is the current cost associated with green hydrogen production and the lack of necessary infrastructure. As of now, the production of green hydrogen via electrolysis is still relatively expensive compared to the production of gray or blue hydrogen. The high costs are mainly due to the expense of electricity from renewable sources and the cost of electrolyzers. While prices are expected to fall as technology matures and scales up, for the time being, cost remains a substantial barrier. The second challenge is infrastructure. The supply chain to transport and store hydrogen efficiently is still underdeveloped. Building the necessary infrastructure for large-scale deployment of hydrogen energy is a considerable task that involves substantial investment and strategic planning. Safety concerns. The other key challenge is safety. Hydrogen, given its high reactivity and diffusivity, can pose safety risks if not handled properly. Hydrogen leaks can lead to fires or explosions, and the gas can cause embrittlement in some metals, leading to structural failures. Therefore, incorporating hydrogen into 3D printing operations requires careful consideration of safety protocols. This includes leak detection systems, proper ventilation, use of hydrogen-resistant materials, and comprehensive training for personnel. These challenges, however, are not insurmountable. With continued investment in research and development, advancements in technology, and strategic planning, the integration of green hydrogen into 3D printing can be achieved, unlocking a new era of sustainable industrial manufacturing. It's clear that the benefits of this integration could far outweigh the challenges, promising a future where industrial efficiency coexists harmoniously with environmental responsibility. The future of green hydrogen and 3D printing. Opportunities for further research and development. There is a vast potential for further research and development at the intersection of green hydrogen and 3D printing. Scientists and engineers could explore more efficient ways to integrate green hydrogen fuel cells with 3D printers, optimize the energy efficiency of the process, and develop safety measures specific to this application. The idea of a closed-loop system using green hydrogen and 3D printing also opens an intriguing area for investigation. It presents an opportunity to redefine the industrial manufacturing landscape in line with circular economy principles. Potential impact on the 3D printing industry. The integration of green hydrogen into 3D printing could have a profound impact on the industry. It would offer a sustainable, low-emission energy source that can potentially drive down the carbon footprint of 3D printing processes. Moreover, it could enhance the operational efficiency and broaden the geographical reach of 3D printing services, even to areas with an inconsistent electricity supply. Conclusion. Summary of findings. The intersection of green hydrogen and 3D printing holds immense potential. Green hydrogen, with its sustainable production and high energy content, can offer a solution to the high energy demands of 3D printing. The integration could lead to more sustainable and efficient 3D printing processes, particularly in energy-intensive areas like metal 3D printing. However, challenges exist, including the current cost of green hydrogen production, the lack of a robust hydrogen infrastructure, and safety concerns. Despite these hurdles, the potential benefits of integrating green hydrogen into 3D printing make the pursuit worthwhile. Final thoughts. As we move further into the 21st century, the fusion of green hydrogen and 3D printing offers an exciting prospect for achieving a balance between technological advancement and environmental responsibility. This intersection promises to redefine manufacturing norms, paving the way for a more sustainable and efficient industrial future. By embracing this potential, we move one step closer to realizing a future where innovation fuels sustainability.